So we're here with Thanos Alexakis today, who's the lead engineer in AVID's Thermofluids and eMachines engineering team. And we're going to talk about electric fans, and that's one of your particular areas of expertise. You've started at AVID doing fan blade design, Thanos. So thanks for agreeing to do this today. When you're doing a fan design, is there a sort of particular process that you would normally follow for a new fan design?
Yeah, so we would start from the blade. That's what delivers the airflow.
Yeah.
And obviously some appreciation of the cooling system is required, just so you can understand the requirement. And then once you have blade design, then that informs the motor design.
Yeah.
And then that informs the electronics and software design.
Okay.
And obviously that goes hand in hand with your space claim limitations.
Yeah.
And then other things like weight and noise. That's very important, certainly with hybrid and electric vehicles.
Okay.
Because you don't have a big diesel engine to listen to, so you have like almost like a silent, very different sound profile motor, traction motor.
Right.
So if your fans are blasting, then that immediately becomes a
noticeable noise. Yeah.
So
you don't want noisy fans.
No. You cannot avoid them completely.
Okay.
Because you are obstructing airflow.
Yeah.
And you try to force it through a ring.
Yeah.
And then that's being then blown against some sort of restriction.
Okay. Yeah.
So there will be noise, but there are ways, to go about it. But it is an important consideration, noise.
Okay. And just to explore that a little bit more, then, what are the kind of things that you can do in terms of improving the noise performance of a fan blade design?
There are things like the annular ring, which is almost like the equivalent of the winglets you see at the wings of an airplane.
Okay. Yeah.
The tipped. Then there is the non-radial blade stacking.
Yeah.
So backwards or forwards swept blades.
Yeah.
That helps. And then there are other things like serrated trailing edges on the fan blade.
Yeah.
These are less common, or asymmetrical blade spacing.
Okay.
But all all these things, they provide a noise reduction benefit.
And is there a trade-off? So if you're aiming for the quietest fan, is there a trade-off in other areas of its performance?
Yeah, there is a risk that the airflow delivery will suffer.
Okay.
Or there may be structural issues. If you have too aggressive 3D shapes on the blade,
yeah,
you may introduce weak spots.
Right.
Structurally. But then, incidentally, for example, when we talk about annular rings,
yeah,
they do provide a strengthening enhancement.
Yeah.
In addition to the noise improvement, for example. Yeah. So yeah, there are compromises and trade-offs. There are some trends, for example. Larger diameter, slower spinning fans are usually better for noise.
Okay, yeah.
Or the opposite, if you're trying to pass a lot of flow through a very small fan, will probably be noisy.
Yeah.
But then, how many fans, how big a fan has system level considerations.
Yeah, it's pretty rare that you'd have. In fact, it seems always to be pretty rare that you'd even have the space that you need for a basic system, let alone the space claim to really add surface area for lots of extra cooling.
Yeah.
That's typically a big challenge, isn't it? Do you see any sort of themes in terms of the requests that you get from customers for new fan designs? What are the trends?
Again, noise.
Okay.
so and low noise, and I think now the customers typically prescribe a speed which is usually slow. It's like, and I think that's to mitigate against noise.
Right.
But then that has an implication on the motor design.
Yeah.
And the electronics as well.
Because you might be trying to deliver higher torque at a lower speed.
Yeah.
Which means typically more current, more copper.
Yeah.
Bigger, more expensive motor.
Yeah. Yeah. So, but that's very typical. So, so there is a firmer noise requirement or specification, and then there is a speed requirement that goes hand in hand with that.
Right.
But that's good, because it's sort of like it frames the requirement straight away.
Yeah. In your experience, and I know you've designed a good number of fans now. What are the main challenges that you've come across?
So the trade-off between noise and performance.
Okay.
Yeah.
So that would be the main challenge.
Yeah.
How do you go about once you've done a design on something like a fan? How do you go about making sure that it's going to deliver consistent performance? So that you've got the initial design, what do you have to do before you launch that as a production product?
A good design process, I think, is central to front loading and ensuring that the fan will deliver on and on consistently. Testing, loads of testing.
Yeah.
Wind tunnel testing. And as much simulation as you can afford within given timescales.
So you're doing product validation testing on the fan. Is there like different manufacturers? Do they have different requirements for product testing, or do you always end up doing basically the same bit of work?
There are usually variations of the same thing. So
right.
and typically those tests refer to some ISO standard, for example.
Yep.
So every now and then there will be a specific customer-driven requirement that's not in any standard document. It's just what the customer has specified internally and requires of the suppliers. So there's nothing particular there that stands out. And interestingly, in the product validation and verification stage, more importantly, the one that you do it towards the end, the functionality, for example, the delivery of flow, that's already established.
Okay.
So what you need to make sure is that after you've done test 1, 2, 3, and 4, and you've passed, then you do a functional test.
That it still delivers the same.
Exactly.
There's no detrimental effect on airflow because of something in there. And then do you often see problems in testing? Do you kind of encounter challenges when you're doing those validation tests?
There are some challenges at the earlier design verification tests. Mainly around validating the blade performance. So the material of the blade, of the prototype blades, is important. So, for example, polyamide-based rapid prototype blades, they may not be as structurally sound because of the material properties or the finishing, like the surface roughness of the blade is not what it would be for like the same as a PA66 injection molded plastic blade, for example, and that has a detriment on the flow performance.
Right.
So you go in the wind tunnel and you don't get what you thought, and you don't know where it comes from. Is it because the blades are deflecting, or is it because the surface finish on the blade is inhibiting your lift performance, things like that. So then can you make a more robust blade from metal?
Yeah.
Yep. Is it too heavy? How do you
Yeah.
So
does that affect the performance
exactly,
again? Yeah.
So these are the things that tend to make a difference early on, but as soon as you go through that successfully, then in terms of airflow delivery, that side of performance validation is easy to manage across the development side.
Right. Yeah. Okay. And what would be, what would be your sort of key tips and advice for a vehicle system engineer who is looking at specifying a fan? Are there any kind of mistakes that you see people commonly make, or?
Yeah. So we have seen a few things. So we have seen the airflow requirement, the number. So sometimes it seems a bit odd or off or a bit too aggressive.
Yeah.
And we have been suspecting for quite a while that the people pay more attention on the data sheet instead of the fan curve.
Okay.
And the data sheet will probably mention like the maximum flow number, but that in most cases will correspond to like a free flow condition, so no restriction.
Right, which you don't have on a vehicle.
Yeah, exactly. Yeah. So that's one common theme.
So be careful about your airflow and restriction.
Exactly. Yeah. So So fan performance need to be discussed and addressed using the fan curve.
Yeah. Okay.
Now, when it comes to electric fans, we sometimes see that maybe the customer is referring to kilowatts of heat rejection versus kilowatts of fan motor.
Yeah.
So knowing which one's what, and
knowing your kilowatts.
Knowing your kilowatts, your kilowatts. So that's my heat rejection, and that's how many kilowatts of a fan motor I need.
Yeah.
And they don't.
Yeah.
So distinguishing between those and knowing your kilowatts. The last thing that I would consider as an important design point is, when we're talking about using the fan curve instead of a single number on the data sheet. Not all that curve that you see on the paper, not all of that is effective. Yeah. So it doesn't mean that you can be anywhere on that curve and that's your fan sorted and working great.
Okay. So is that because fan blades tend to have quite a narrow efficiency window? So you've got like one point where it's efficient and then it falls off quite quickly either side of that?
Yeah. So there is what we call the unstable region of the fan towards the the higher pressure, lower flow rates. Then there is like the stall region.
Yeah.
So it's very important to have a system restriction curve and then map that against the fan performance curve. Yeah. And if that intersection point it's too far on your left, then give someone a call and because you might think, oh, actually if I just fit a huge fan, it'll be fine because it's going to have more airflow than I need, and that's great. But actually you could end up in a situation where you're not getting any airflow because you're running the fan so slowly it doesn't actually generate the pressure to go through the system. So over fanning your system can be as bad a thing as under providing for it as well. Yeah, or a wildly a very poor efficiency for the fan. Yeah, exactly.
And because they consume. I mean, fans generally are not massively efficient, are they? So axial fans. So you're looking at a lot of power consumption on an EV. I guess it depends on the kind of EV. If you've got ram air or no ram air, but it can be really high power consumption figure for the you know, parasitic loss on the powertrain.
Talking about ram air, another interesting design challenge, and maybe because we come from a heavy-duty commercial vehicle background where there's no ram air, is how do you manage a freewheeling fan under excessive ram air?
Okay. Yeah.
Do you make it run as a wind turbine? If you do that, then your software, your hardware needs to be tuned to sustain that. I think it's called fourth quadrant regenerative mode.
Yeah, so if you basically, the fan is being spun by airflow.
Yeah.
So this is something called windmilling.
Yep.
So then if you just let that spin up, you could go too fast and damage stuff. But with the kind of motor that we have, you're generating, effectively you could be generating power, but then that creates drag.
Yeah.
So what's the strategy to control the fan speed to prevent damage to the system, but also not to minimize drag on the vehicle, I guess.
Yeah, and if there is any amount of DC current generated back into the system, how that does that need any management?
Yeah.
Is it circulating around the system? It's these types of consideration. The other thing is what the team was describing to me recently is that drag that is also following a curve.
Yeah.
So depending on your ram air and your fan speed, it doesn't necessarily mean that you always have a lot of drag. You may not have a lot of drag because that's subject to a curve as well.
Yeah.
So it's
so you could, in theory, you could move the fan into an operating speed relative to the vehicle or the ram air velocity, and effectively cancel out the drag of the fan blade just by holding it at the right operating point. Yeah. And is there anything that you think that a vehicle designer or a system designer could do at a vehicle system level to basically make life easier for the fans, to improve the fan condition? What are the key things that they should try and take into account?
So system restriction on the on the direction of the flow, on the direction of flow. So usually actually, the proximity of components upstream and downstream of the fans, the grills and the density of the radiators and how close these are, and it will be different for different fan designs.
Yeah.
So that's key, and that then will affect the noise performance and the fan size and the fan efficiency. The other consideration is how uniform the flow is across the radiator pack, and whether that's important or not. For example, do you want an array of many fans or an array of not so many fans?
Yeah.
With passenger automotive, crash and where the fan is and how many fans you have is important, for the crumble zone and what ends up being passed on to the passenger, basically, in the event of a crash. So these are interesting things that come up.
Yep.
Windmilling is interesting. So we have been...
Especially some of because you're on a couple of programs where the vehicles are going
400 kilometers per hour.
Kind of slightly fast.
Yeah.
So not a massive issue on a bus. In fact, not an issue at all on a bus. No. The cooling pack's normally at the back, so there's no ram air. But some really exotic HEV programs with very, very high vehicle velocities. Yeah. So 400 kilometers an hour is that's moving.
Yeah, and the aerodynamics of the whole vehicle and your floor regions, around and through the vehicle and the fans and the cooling system. But this all becomes very challenging and interesting and hard to get your head around in such a fast-moving vehicle.
Yeah.
We have seen, weird flow and pressure figures for these type of scenarios.
You get some strange phenomena, aerodynamic phenomena building up. Yeah.
So, understanding your pascals and cubic meters per second and where those happen and how and why. Yeah. And the system restrictions, that's really important, certainly in a very in such a high speed scenario. The other thing is, in the spirit of being creative, we have seen people putting fan systems at the rear of the vehicle.
Yeah.
And after a certain speed, after a certain vehicle speed, that's also problematic because you create like a zone of no air to pull air from the back.
Oh, okay, right. So like a negative pressure or low pressure zone. Yeah.
So there are things like that. They don't come up very often, but they do come up.
Yeah.
So
it's always a lot of trade-offs at a vehicle, particularly passenger vehicle level, with vehicle styling, vehicle aerodynamics, and then thermal systems. Like those are the key kind of headbutt topics of the stylist wants one thing, the cooling guy wants another thing, and the aerodynamics guy wants something completely different. And trying to make all of those things overlay and actually make something that works, especially at 400 kilometers an hour, is really a big challenge. Yeah. Okay, great. Well, thanks very much for that. Really appreciate you taking out the time to do this today.
Thank you.
Great. To find out more about AVID, contact us today. If you have enjoyed this video, don't forget to like it and subscribe to our channel for more updates.